We're Team 26033, Plastic Recycling, Carbon Capture, and Disaster Relief through Pyrolysis. We're sponsored by Peak View Environmental Solutions. I'm Max Bannock. I'm a biosystems engineer, and I'm the team lead.
I'm Aurora Rivera. I'm a biosystems engineer and I'm the procurement lead.
My name is Anthony Castillo. I'm an industrial engineer and I'm the safety lead.
I'm Don Klein. I'm a biosystems engineer and I'm the fabrication lead.
I'm Zach Schiffler. I'm a mechanical engineer and I'm the mechanical lead.
My name is Alexis Munguia. I'm a mechanical engineer and I'm the research lead.
My name is Carlos Correa. I'm an electrical engineering student and I'm the electrical lead for our team.
Our project is a mobile plastic pyrolysis system that, in an oxygen-free environment, heats plastic to 500 degrees Celsius to thermally decompose the plastic into hydrocarbon vapors, which are then condensed into a crude pyrolysis oil. So the purpose of this project is to create a mobile pyrolysis system that is field deployable to remote, disaster-prone or communities with poor waste infrastructure, to provide them with a way to take this waste and turn it into a usable source of fuel.
So the main part of our fabrication process started with our inner reactor, which was made of stainless steel, and we procured it through our sponsor's fabrication contact. It took around a month to arrive in our hands, but after we got that, we began from there purchasing fittings from McMaster Carr to go up into our condenser and into our filter stack. The frame of our system was mainly welded by Zach, Max, and myself. That was MIG welding for 1-inch steel beams sourced by IMS, Industrial Metal Supply. So a big part of our fabrication process was working with Mike Mason up at the Agriculture Center. He really helped us out with a lot of the TIG welding for stainless steel, as well as some of the other fabrication design considerations.
Our process starts here at the nitrogen bottle. Nitrogen is flowed through this tubing into the reactor. The reactor is where we house our plastic feedstock for processing. It's heated up by these heating coils, which you can see here, and then insulated further by our wool insulation. As our pyrolysis vapors are processed, they rise up out of the reactor through our plumbing here, passing the pressure relief valve and the pressure gauge. They flow into the condenser, where they're condensed into a liquid state, leading into our fuel collection container, and the gases rise up through our filter here. This port allows us to flow oxygen into our sensor here to ensure that our oxygen level is below 2% to avoid combustion. This is our water reservoir, which holds the coolant for our condenser.
Our control system is comprised of 5 main components, which are the PID controller, solid state relay, emergency shutoff switch, power button, and volt amp meter. So these components work together along with 2 thermocouples within the reactor body to display and regulate temperature based off of set values desired for a pyrolysis reaction.
So one of the most important analysis that we had to do for our senior design project were heat transfer. We had to ensure that the inside and of the reactor and the outside of the reactor were good. For the inside, we had to have around 400 Celsius, and for the outside, the safety standard says that we cannot have more than 34 Celsius outside. We also had to do a stress analysis for the reactor to not fail, because we were gonna expose it to high pressures inside, and the difference in pressures could actually make the reactor fail. So the third analysis that we did was the oxygen purge. We had to install a nitrogen tank directly to the reactor to ensure that the oxygen levels were less than 2%. I performed an analysis using theory of how it would look, and I also did an analysis once we did the verification, and it exactly matches what we were expecting to do.
All right, so here we're going to plug in our 10-volt wire into our PID controller to heat our heating coils to 100 degrees Celsius.
Temperature monitoring verification is meant to verify our software implemented temperature monitoring system, which consists of an Arduino Mega 2560, a TFT display, and MAX 6675 modules, communicating through an SPI communication protocol. To verify this system, we compared the PID controller read value to the displayed values and ensured it was within plus or minus 10 degrees Celsius at 100, 300, and 500 degrees Celsius. Our emergency shutoff verification consists of getting the reactor up to temperature, then activating the emergency shutoff switch. which cuts power to the PID controller and reduces the control signal for the solid state relay down to 0.
Good? Yep. That was less than 2 seconds. Okay, so for our purge verification, we use nitrogen, running it at 30 liters per hour through our system in order to achieve a less than 2% oxygen within the system and maintain that less than 2% oxygen. For our verification, we were able to achieve less than 2% in 7.5 minutes. For our pressure relief verification, we increased our nitrogen flow to 100 liters per hour and used a ball valve to simulate a blockage in the system. This allowed us to pressurize the system to 1.34 atmosphere and engage the pressure release valve. Through testing, we were able to verify that the pressure release valve activates at 1.33 atmospheres. For our consistency verification, we wanted to determine if our system could thermally ramp efficiently. So to do this, we tested that our system could get to 100 degrees Celsius and hold for 5 minutes, then 300 degrees Celsius and hold for 5 minutes, and then 500 degrees Celsius and hold for 5 minutes. So we were able to successfully do this within the 100, 300, and 500 degrees within a plus or minus 10 degrees Celsius.
For burn prevention, any surface exceeding 35 degrees Celsius, we want proper PPE or signage placed. And so our results showed that our outer surface was 78 degrees Celsius. So therefore, welding gloves will be needed and proper signage such as hot surfaces and authorized personnel will be present. Due to the portability system requirements, our system needs to be less than 160 kilograms, which is the NIOSH standard for a 5-person carry. The weight of our system was then verified at 109 kilograms. The system requirement was for our system to be transported in a standard bed of a truck. Therefore, it needs to be less than 135 centimeters by 185 centimeters. And our whole footprint of our system measures 83.82 centimeters by 126.365 centimeters.
Now that we have verified all of our system requirements and proved that our system has the ability to process plastic feedstock into a crude pyrolysis oil, we were able to look beyond to our stretch goals, which were to physically process a plastic feedstock into a liquid fuel. By our sponsor's request, we were able to deliver our system to them so they would be able to process a PP and PE plastic feedstock mixture of plastic pellets and then collect the liquid fuel. After putting in 2 pounds of this feedstock, we were able to collect 1.87 pounds of this liquid oil, and this achieves a 94% pyrolysis reaction efficiency and a 73% overall efficiency. As procurement lead, the budget was carefully managed by detailing all expected parts for each subsystem in advance. Of course, we purchased more items along the way as we realized we needed new fittings and connections or had to troubleshoot. Eventually, we began purchasing individually so then we could request more reimbursements in order to smooth over the procurement process and adhere to our tight deadlines and our schedule. Along with the system, we will also be providing a care package of materials that are to be replaced over time, including gasket material and ceramic fiber insulation because these materials degrade over time with use. We will also be providing a standard operating manual so that the users that are going to be operating this can become accustomed to the safety as well as the functionality of the system so that they're using it accurately and safely with no injury.